Hello and welcome to the section on build tools, I/O, and error handling. We're going to get to know the Go toolchain a bit in this section through the Go command. We'll see how to use the flag and OS packages for some CLI apps that read input when invoked and from the environment they're running in. We'll do a good deal of file and directory handling, and we'll end with some good practices around error handling. I'm excited to show you more as we get increasingly comfortable with Go. Speaking of getting comfortable, let's talk about the first video in the section. In this video, we're going to get comfortable with the Go build tools through the Go command. We'll take a closer look at what's involved when running and building our programs, and we'll learn how to cross-compile our programs for a wide range of other platforms. We'll look at ways of pulling up package documentation locally without the need to navigate to the online documentation site. We'll talk about dependencies and take a look at where they are downloaded and installed on our system. We'll also see how to interrogate our source code to understand the dependencies that are in use. Lastly, we'll see how vendoring keeps our programs from breaking when there are changes to packages that we depend on. Let's get started. Working with the Go toolchain primarily involves invoking the Go tool from the command line and specifying some commands and flags to get a desired outcome. The Go tool invokes other programs behind the scenes as appropriate. We can get a quick view of all that the tool has to offer by entering Go or Go help as a command in our terminal. The Go tool invokes other programs behind the scenes as appropriate. We can get a quick view of all that the tool has to offer by entering Go or Go help as a command in our terminal. We'll cover the commands that you're most likely to work with regularly in this video. I'll start by checking my Go version. Next, let's see what environment settings that the Go tool works with using goenv. When we compile, run, or build programs, as we have done in previous videos, those executables are made for the OS and CPU architecture on which the program is built by default. Go figures out its information through the Gorch and Goose environment variables. The Go path represents a workspace that Go will look for source code, create package artifacts, and install binaries in. If I navigate to my Go path, you'll see an src, pkg, and bin directory. The src directory contains the source code that Go compiles. When I list out the contents of this directory, you'll see the start of what your typical import paths would look like. That means that if I navigate to github.com/boltdb/bolt, that will be the source code used to compile this package when I import it. When you compile your packages, those compiled binaries are stored in an archive format under the pkg folder. Such is the case for our boltdb example here. That code is referenced when I import the package, and that saves it from having to also be recompiled whenever I make changes to my own program. The bin directory is where executables from packages that you install get placed, meaning that if a package has a main package that leads to it building into an executable, when I pull this package through go-get or go-install, those executables will be placed in the bin directory. Let's talk about run. You've seen me invoke go-run countless times now, which just compiles a program before running it. This works with projects that have a main package, making them runnable as executables. Non-main packages cannot be run as they are designed to be imported instead. Let's see what I mean. In this package, I have a main.go file with the package main declaration at the top and the main function entry point into the program. Using go run on this program will successfully compile and run it because of this. Now let's switch to a different package which has a go file without the main package and entry point. When you attempt to run this program, you'll get an error. This makes sense when you look at the package's code. It is designed to be imported and used as a library and not as an executable. Now let's talk about build. Unlike run, you can build packages meant to be used as executables and packages meant to be imported into other packages. The difference is in what the Go tool does with the resulting objects. When you perform a go run with the X flag, note how the program is compiled and run from a temporary work directory on your file system. In the case of go build with the X flag, the difference here is that the resulting object is relocated from the work directory into your program's parent directory, taking on the name of that directory. You can also override the name of the resulting program with the O flag. The build command has quite a few options available, but let's focus on one aspect that you may come to use regularly, and that's the LD flags option. Say I want to compile version information into my executable. One way to do so would be to set a variable in my main package that I can override during the linking phase of my program's build process. Build will produce an executable with the version number built in. As you can imagine, this technique might be very useful in automated build situations where you might tag each build from your CI/CD pipeline with a version before sharing it with the rest of your team or the outside world. Speaking of sharing, let's talk about cross-compilation. Go has the ability to build programs for operating systems and CPU architectures other than the one you're working in. You can tell your own OS and architecture simply by doing a go env on the command line and seeing what the goose and gorge values are set to. When we want to create an executable for a 64-bit Windows OS, we need to only change the goose and gorge values during the build. Here, I'm building a 64-bit Windows exe where I also override the file name of the program to something familiar for Windows users. You can get a complete list of the OS and architecture combinations in the Go documentation. Speaking of documentation, while it is common to use godoc.org to look up package documentation, let's look at a couple of other ways to pull up the same documentation locally. The first is simply running a local documentation server using the godoc tool. You can then navigate to localhost on the port you specified and have something that looks similar to the actual golang.org site and navigate through to the documentation from there. The next way to pull documentation is in a more specific manner using the doc command from the Go tool. You can invoke it like so. This will list out the same package documentation that you've seen before. You can get more specific by using a Go syntax-like way of looking up the documentation. Go doc funct println will show you the documentation with a println function, for example. A useful default behavior is to show documentation for the package in the current directory. By default, only exported symbols will have the documentation shown. You override this with the U flag, which will allow you to see any documentation you might have for unexported symbols in your packages. In your day-to-day work with Go, you'll find it useful to pull in external packages that solve specific problems for you, be they packages containing executables that you can just run locally, or packages that you can use in your own code by importing them. For example, I like to use a package called graphpkg to show me a visual representation of package dependencies. To retrieve and install a package, I perform a go get on the package's location, and the package is downloaded and installed, thereby making the binary graphpkg available from my gopath/bin folder. The go get command has multiple flags you can explore, but one you may find useful on a regular basis is forcing the download of a package you already have locally to ensure you have its latest version. Here, I also throw in a verbose flag so that I can get a printout of all packages being installed. That includes the dependencies of the package. I can then invoke it like any other command line tool. Speaking of dependencies, the go list command is what you want to reach for when you need a listing of the packages in your program or library. Simply running go list in my current package directly is not super exciting given the simplicity of our program, but we can get more information out of this tool using some flags that I find useful, the format and JSON flags. The format flag allows you to specify a format for the output. Looking at the documentation, I see that I can get a listing of the import paths used by this package. Let's try this. The output looks accurate based on our program. The JSON flag dumps out a great deal more of information all at once. Let's touch on vendoring. When you use go get to retrieve a package, that package and its dependencies are placed in your Go path. That may be fine in the short term if you're writing programs that depend on and use the same versions of those packages. But over time, as updates come out and the packages start to evolve or change, breaking changes may be introduced or existing behaviors may change. When you update those packages in your Go path, you may start to find that your program stopped compiling due to breaking changes. That's where vendoring comes in. It allows you to keep a project local set of dependencies in a vendor directory where the build tool looks first before looking in your Go path. To see how this works, I'll use a dependency manager called dep to manage this process for me. At the time of recording, dep is an experiment of the Go language, but not yet the official dependency management tool, but I expect that to change. Let's see it in action in my program. Given a program that makes use of an external package called things, I want to make sure that the version of the package that I'm using won't break my program should its functionality ever change, so I'll vendor that dependency. With this command, dep will pull down the latest version of that package and vendor it. Now every time I build my program, I can rest assured no breaking changes will sneak in. No coverage of the Go toolchain would be complete without the test command, but we will have a dedicated lesson for testing your code where I'll dive more deeply into Go test then. That's it for this video. We covered the Go toolchain through the Go command, took a closer look at what's involved when running and building our programs, learned how to cross-compile our programs for a wide range of platforms, learned how to pull up documentation locally, talked about dependencies and how vendoring keeps our programs from breaking when there are changes to packages that we depend on.